is in fact infinity, but because of Yomdin theory, or at least the way we understand it, you can use it when you want to make finite time statements. You can use it only. You can use only finite differentiability. Okay, so you think this is a large integer. So when you have a map, a differential map, either F or in fact, we will be interested in its protective extension. You can, in some sense, optimize its Lyapunov, its Lipschitz constant by iterating. Okay, we saw that in a lot of situations, you take advantage of the sort of homogeneity of the entropy by having an estimate up to some back constant, and you apply it to a higher order iterate to get rid of the constant. This would bound the Lipschitz constant of Fn, and then it's a multiplicative. This one is a multiplicative sequence, and so the limit exists, or you can take the lim suit if you don't want to think about it. Okay, so now the dilemma. Okay, so we start from some measure. Invariant for the projective dynamics. Okay, so which is a hyperbolic in this sense. I mean, not hyperbolic as with respect to f hat, but in the sense that it lives on the stable and unstable graph. So in particular, the projected measure will be hyperbolic almost everywhere. Okay, so that you give yourself this, and you have two small parameters. The one you should think about it as just a spatial scale, and eta will be the error that you allow in your estimate. Okay, then. Well, it's always, of course, you can project, and then it's a lift. Any line measure here is a lift of its projection. Okay, we will apply it. And this is exactly saying that the projection is hyperbolic almost everywhere, up to the lemma we saw last week. Okay, so in fact, for what we are doing now, I mean, yeah, the main case of the lemma, we in fact, we have the fact that mu hat is some lift, not necessarily ergodic, an ergodic hyperbolic measure. So we are certainly in this setting, in something a little bit more constrained. I just formulated it in this way because, well, at some point, maybe not today, I will explain the general statement, and this is one of the things that will change. That we will have to remove this restriction. Okay, so we have then what the lemma tells us is that we can choose gamma small enough. So it's here I just write it like this. I should write there is a gamma 0 depending on mu hat, delta, eta, and R for the quantities given before, such that we have the property for gamma between 0 and gamma 0, but I don't want to. I want to write something that I can understand, so I simplify this. For all integer n large enough, okay, we can find scales, so a double scale if you like, okay, which will be as small as we wish because we have this parameter delta at the beginning. we will have an open set, so a subset of the projective extension, open, which is large with respect to mu hat. Yeah, and since we are interested in measures that converge to mu hat, then we want this guy to be true for nearby measure. So we will impose that the boundary has zero measure, so that mu hat is a continuity, well, semi-continuity point for the measure of mu hat. Okay, that's okay. Then we will have some large integer. Okay, with the following property. Yes, and if we take any regular CR curve, so sigma is a CR map from zero from the unit interval into M, whose derivative does not vanish. This is what we mean by regular. It is CR, and with CR files, less than these two scales. I remind you, it means that all derivatives of sigma up to order R are bounded by epsilon. Now you have a lift defined by the natural formula. Okay, since this doesn't vanish by the regular assumption here, this is really a curve on the projective bundle. It is a TR-1 curve. So here what we ask is that all derivatives up to order R-1 are bounded by epsilon hat. Okay, so if we take any such curve, then what we are going to do is to find reparametrization so which will be smaller in this sense of admissibility that I will recall.
Is the curve in your
Yes, it will appear soon. But so parametrization Rn is a set of affine maps from the unit interval to itself, so that you let me write it. Okay, let me finish write this, even if it's sigma tan n over some subset T. So here, let me recall what is a parametrization. Okay, at 2 times 2.5. Okay, no, I don't need to get that now. What we did is simply I have T is a subset, I didn't say it now, of the abstract curve, okay, the domain of sigma. And what you want is that if you take all the maps in your parameterization, then the images cover the set T. In other words, what happened is that when we apply this, we'll be only interested in and actually only able to control typical points for the measure, not all points on the curve. So for this reason, we won't be following the whole curve as it evolves under F, but only some part. Okay, and this to say that we are looking at a parameterization over T means we only care about the part sigma of T of the curve. Okay, so that's okay when you so this.
Where is T qualified?
Sorry.
Where is T qualified?
So okay, for any T, T is going to, I'm going to give even better than the quantification. I'm going to give a formula. Okay, so here just to finish this, let me make a picture. So this is sigma. This is 0, 1. So you think that T is some arbitrary subset. It doesn't have to be smooth or whatever. In fact, it is probably more like a control set. And this is T. And your curve is from 0, 1 to sigma. And now the parametrization, or in fact, I could say reparametrization, but I found that parametrization was long enough already. That if you have other copies of the unit interval, and you have this map psi, and you want, okay, I should have used another color. You want their images to cover the blue set, the set T. Okay, so that if you think of the curve here was the image of sigma. And if I give you a parametrization over T, I will be, in particular, this will imply that the union of the sigma composed with pi, the union of the images when pi ranges over the reparametrization is the set here, okay, which covers the image of the blue set. Okay, in my application, the image of the blue set will be the some iterate of some points with good estimate after, let's say, of Birkhoff ergodic theorem, and I will keep track of those to control the entropy. So that's what a parametrization of our subset here is. Okay, so what is this quantitative notion admissibility? It means that we are looking at things of size at most epsilon, epsilon hat, but not only for these things themselves, but for the iteration. Okay, and okay, so I will first write it like this. That you want all this to have CR size. So these are again regular curves because okay, I said affine map, but it's affine non-constant, of course, and there would be no point. Okay, so again, this is a regular curve, so I can lift it and I can ask that its CR size is less than epsilon hat. So for all the iterates up to n. Okay, and now there is a little extra twist, which is that you have this number n, because for some technical reason, we will have this estimate only at certain times. So, in fact, what we have is that for each side, there will exist a sequence of integers of times, starting from 0 and going to n, such that the gaps are at most n. Okay, and at these times, we control. So we have, okay, we are in the setting of Yomdin theory. We want to compute or to bound entropy by bounding a number of curves of small size in the CR sense. Okay, and we need to do that not only for the final image, but at all times. Okay, and now, so the size has to stay constant, but actually what is natural, even if in the end we could just pretend it's true for all iterates, is that you have some times where you really have control, okay, and in between things can get a little bit worse. Okay, so you allow these gaps. CR size is less than epsilon. Okay, and I said, so this means that the CR size of sigma itself is less than epsilon.
The word size, not symbol.
And this one,
describing properties of an object that you will construct?
yes, we will construct. We will together construct the friend. Okay, so what is the set T? So the set T is the set of parameters. Okay, really it's the set of points. In the curve, which so that we really have a neutral block. This is what we want to talk about. And there is an extra condition about this U hat, which is that the fraction of the time, the fraction of this iterate so this is the neutral block, and the fraction of the time, the fraction of the iterates which belong to U hat is bigger than 1 minus gamma. So so what happened? So in fact, this U hat will be the set, some set where we can use some modulus of continuity of the unstable direction. okay, that we will need. And so this will be where we can actually transfer the estimate at one point, okay, to a small curve around it. Okay, so so I have a reparametrization over some subset, okay, that's always true. And this thing, I don't know if it's going to be visible if I write it down. So let me write it here. Okay, so the big estimate with the cardinality of this reparametrization will grow, but only slowly. So some number, this kind of log of the Lipschitz constant of the projective extension, but divided by R-1, the smoothness of this expansion. This is typical Yomdin theory. Up to some error. This is the parameter theta. And I forgot to dash on and bigger than this threshold. Okay, so what we are saying is you give me a measure on the projective extension, which comes from a hyperbolic measure. You fix me, you tell me I want to look at things at a scale smaller than beta, and my error should be in the final estimate should be less than beta. I say very well. Then this is the double scale at which you have to work. I give you an open set with big measure and a minimum size, minimum time that I need for my estimates to become effective. And then I have the estimate, which means the following: for any regular curve with small CR size, okay, the part on it which is neutral and which sees a good proportion of the time this open set you have, you can cover it by a parametrization such that each piece has small size in the same sense, and cardinality that grows only slowly. Okay, slowly because R is we are going to take it arbitrarily but big. So therefore, this will be arbitrarily small. Okay, some question about the statement. Okay, it's really, we proved, I don't remember when, that that we had neutral blocks for a fraction 1 minus beta. Okay, and this is good. This is the key tool to tell us during these blocks the curves, or at least the points on the curve that we're interested in, they don't really grow. Okay, so that's. Let me make sure I don't skip. Okay, so now the lemma. The dilemma for proving the dilemma tells us that in this setting, there exists indeed, we are going to build the open set, you have. And find the scale arbitrary or double scale arbitrarily small. In fact, smaller than this. So we will choose it less than this delta, certainly, but also less than, so to work, Yomdin needs the scale to be small enough, it is epsilon y. And furthermore, to make sure that we can, that up to some error given by theta, we can control the growth on a small curve by the derivative taken anywhere in this small curve. So essentially, through the modulus of continuity of the curve with small CR size, okay, this gives us another. Okay, so this is a given. This is Yomdin. Okay, this is to relate. Length. I will leave the statement, but later. Length when we will use it. Length and derivative at any point of the model. Okay, so small with the following property that if you take any 2 points in this open set which are close, epsilon hat close, I could say. So this means that their projection is epsilon close. So here I'm writing in order not to die of this. Again, the point themselves, they are epsilon hat close. So if you are in this situation, so the points are epsilon hat close, and both inside the open set, then for all iterates up to n. So here, for now, sorry. The points up above stay close. Epsilon hat close. Okay, that's the lemma. Okay, so how do we do that? Okay, so as I said, we start by using the measurability of the unstable space. Okay. We apply Buzzi's theorem, which will give us a compact set with big, arbitrarily big measure. Here I'm inside M, so I'm looking at the projection of mu hat. Okay, so I have this, okay, so with big measure and the following property. Yeah. Okay, and so that this. Okay, so let me look. No, sorry. So let me take, sorry. Okay, let me take epsilon hat as in the statement. Yes,
This case, the statement,
yes.
is it M?
No, it's a compact set, but let me.
The distance of the iterates FK.
Okay, oh, no, it's not. Oh, sorry. Here, yes. Sorry. Anyway, I like. Well, I'm used to that K means some iterate before N, but here we have this new K.
Maybe I am missing something. You on the left side of the implication, you know the points are close. And on the right hand side, the trajectories are close. Under that assumption. On the left hand side of the
So you want to
2 points.
Yeah, 2 points.
One which are close.
which are close, and you.
White trajectories.
We're gonna spend the plane set.
Okay.
Like a special section then.
Let us see.
You're in a special set.
Let us see.
Okay, but you started.
Okay, let us see. Let us see the proof. Okay, so then this is why you have two epsilons. Exactly, because if you. Okay, so
something absolutely trivial. You have on the left hand side of implication that points are close.
okay, let's do the proof, and we'll see.
That statement. Understand.
So let me.
You have neutrality or something.
How
How it is possible to
let. So you're right, there is something wrong. Okay, let me.
is a key.
Yeah, it's all quantified.
Okay, so let me.
Neutrality is.
Okay, because what I'm troubled now.
Maybe it's a good time for a break. Oh, it comes from all integers at zero.
No,
But you have depends on capping.
sorry. I didn't hear.
You have depends on capping.
Yeah, you had depends on N. So yeah, you had will be some neighborhood of K. Okay, so let me. Okay, what? Yeah, let's take a break now. Okay, so here this lemma. So opinions are divided. Some think it is trivial, some think that it is impossible. So it's very good. Okay, so what I should point out is that it's not trivial because we want the same scale epsilon hat here and here. I mean, of course, if here we could put a smaller number, we would just be saying that f hat is continuous, which it is. Okay, so that's one remark. And the thing that we are trying to do is to say, okay, remember this ball at a double scale. It's what a set of points such that the projection are epsilon close, and the points above are epsilon hat close. Okay, we want, I mean, we want more because we are dealing with parametrized curve, but one of the things that we want is to, at every iterate, or at least at each good iterate, we want to control things to be inside a given ball like that. Okay, so each time we iterate, before we iterate, we have done what it takes to ensure this type of condition. Then we iterate. The map, of course, is not a contraction. Otherwise, all the entropies would be zero and there would be nothing to talk about. Then we have to subdivide our ball and make sure that we stay at here. And during a natural block, we want to say that up to some maybe very slow subdivision, we have this error term, if you wish. Up to some few subdivision, we are able to, when we have this before the iterate, we will again have the same estimates after. Okay, and in particular, this lemma tells us that if we start from points inside which are epsilon, epsilon hat close, then the directions will still be epsilon hat close. Okay, so that is why we want to prove this. So now let's prove it. So we start by saying, okay, these maps are the unstable direction is measurable. Okay, so now we fix epsilon, sorry. Okay, so we have our number n. And now so we first pick a compact set on the surface with big measure, okay, on which okay, so maybe I should not write it like this, on which if you take 2 points on the surface which are epsilon close, then they are lift to the unstable lift. Okay, let's see. This is x with the unstable direction of x are close. And not only then, so they are close. This lifting to the unstable direction is the measurable part. It is where we need the losing theorem. Then we apply. Okay, we want to control things up to iterate big N. So we apply f hat, but f hat is clearly a continuous function. So it's not there. Things happen. And same thing for y. We are looking at. Okay, so by losing theorem, since the unstable direction is measurable, there is a compact set with measure arbitrarily close to 1, on which this function becomes continuous. So the composition with some iterate of f hat is also continuous. So we can find, if we are given, if we pick some epsilon hat, so I'm just a little bit, okay, so sorry, we don't want to pick it yet, to pick it here yet. So here we just say, okay. On the compact set, the function x goes to fk hat of x plus x is continuous. Okay, that's the first thing we want to do. Now we have our graph gamma plus and gamma minus. Okay, let's focus on gamma plus here. So we know that mu hat is concentrated on their union. So now you can just look at k hat plus to be the graph over the restriction of the graph over k. So that's okay. Let me for now ask the same. I'm not sure if we need it for the stable set. Okay, so we have this k hat plus, this k hat minus. Okay. And together, of course, they have mu hat of their union is just a matter of k. Okay, because mu hat lives on the union of the two parts. Okay, so now as long as we are on the graph, we have this formula which tells us that okay, it's just the equivariance of the stable and unstable directions. Okay, so now what do we do? Now we fix, it is now that we want to fix epsilon hat. So what do? We want it to be less than this quantity. Okay, so some this is given, this is Yomdin, and the last one is related to it's not the last. So this one is that we want to control the length by the derivative. Okay, so it has to do with the modulus of continuity of the differential. I don't want to get into it now. Okay, and finally, here we can put the distance between the two compact sets, okay, which are two compact subsets of the two graphs. So this distance is positive. Okay, so that we know that when we take 2 points which are epsilon hat close in the projective extension, okay, if we know that they are in the union of k plus and k minus, let's do it k hat, then they have to be both in k plus hat or both in k minus. Okay, so we have, let me check. We have this epsilon hat now. Okay, so now we use the continuity to find epsilon. This gives epsilon, okay, with the property that if we are exactly in this set, okay, it's just the modulus of continuity over k, then this implies, okay, what I had written before, but too quickly. Okay, Okay, the unstable lift. Epsilon hat closed for all up to the iterate big N. Okay, you could think for now that big N is equal to 1. It would not really, change any idea. Okay, so we have this. And now what we see is that, okay, because of what I said, if you take any 2 points now in K hat, which is the union of K plus and K minus, if you have that the distance between X and Y is smaller than epsilon, and the distance between the 2 points themselves on the projective bundle less than epsilon hat, then we get what we want with, sorry, here we still need some margin. Okay, we get what we want, so that is for all. Okay, just this extra condition tells us that the points, okay, we know that they are in one of the two graphs, the stable and the unstable, and this condition is just used to say that they are both on the stable or both on in the unstable graph. Okay, since we are looking at compact subsets which are at a larger distance. Okay, so that's the thing, and now we use a compactness of N hat to see that we can enlarge, we can replace K hat by a small neighborhood and still get the same conclusion, but for epsilon now by compactness. Yeah, there is some small distance so that we can just enlarge K hat into its U hat, which will just be some small neighborhood of K hat with the two conditions. Then we will get that this over iterate, sorry. Okay, you pay a little bit because it's enlargement, so you will get that the distance are smaller than epsilon. Okay, to see it, if you wish, you proceed by contradiction, and you will obtain two sequences that converge to K hat, which violate this condition, and you realize that the limit points would violate this one. Okay, so
use here the fact we are close to EU, and
yes.
If we were close to ES.
Okay, so here this condition, it's just there because we have it, and because it tells us that either we are close to gamma plus or we are close to gamma minus. But both, so sorry, what I mean really, both points are close to gamma plus or both points are close to gamma minus. Okay, because of course the stable and unstable direction, they are far away.
Let's try to understand what is the mechanism, because if we are close to gamma plus unstable, then directions and So they are by hyperbolis at the close. Maybe we don't need to use.
No, it's not. It's just what using theorem. Using theorem tells you that these things. Sorry.
No, okay. Using this ornament.
Here we, as I said, we iterate, but it's not really the.
I'm still
This is-
thinking how you jump from base to derivatives.
Exactly, by saying that we live on the graph. Okay, imagine that the stable and unstable graph. Well, no, not at all.
If you don't use Yomdin, maybe the mechanism is that you are close to unstable, so in the
No,
projective space it is attraction.
no, no. No, here really we are, well, what we are using is that, so and this involves what you are speaking about, is that the measure is concentrated on the two graphs. So if you, so this comes exactly from what you're saying.
Okay, so if
You are,
if it was on E minus, would you use ray images?
no, you have continued. Once you know that you are concentrated on the graph, exactly for the reason you said, because you have two distinct Lyapunov exponents. So the only invariant things are the stable and unstable graph. Okay, now these two graphs, if they were graphs of a continuous function, you would just say, okay, this is, you use continuity. So I am on a graph. So everything depends only on the base point. So since I have assumed that things are continuous, if the base points are close, then but you iterate a fixed number of times. Yes?
I was going to ask, epsilon depends on n.
Yes.
If n is big, epsilon is very small.
It depends on big N,
Yes.
but big N is small, as usual.
Yeah, okay, that's why there is no problem.
If we choose epsilon up to n, then of course there is no problem.
In fact, big N is chosen only to kill things like the difference between lambda of f hat and the supremum of the norm, and to kill the Yomdin constant that appear in the estimates.
So it is not one use it to exponent or anything, just to kill R.
Big N, yes, big N, yes. So big N is a little bit trivial. This is why I hoped to not to discuss it. So here, yes, it's really not about iteration. You can think about if you understand this lemma for big N equal to 1, it's okay. And even big N equal to 1 is very, well, big N equal to 0 will not make sense. But big N equal to 1, I mean, really what's going on is, okay, so let me just repeat it quickly, concisely, hopefully. You are on graphs. You know that you are on one of two graphs. Okay, so if these graphs were closed, if the function was continuous, then you would just say, since the function is continuous, I need to know that I am on the same graph, so I am not too far away. This is how I use this condition. And then it's just continuity. I want to be epsilon hat closed. So here I put epsilon, which is much smaller than epsilon hat,
Okay.
but I don't care.
All are constant. You don't
Well,
add to infinity.
yeah, here the point is not the iteration.
Okay.
The point is that you have to first choose epsilon hat,
Okay.
which comes from this continuity problem and the distance between the two guys. And once you have chosen this epsilon hat, you do these things to know that you are on a continuous path, and modulus of continuity gives you epsilon.
Look, in the statement, epsilon star is not relevant.
It is because we want to, we will use it.
Later.
Yeah. So to prove this, we don't need. But you see that epsilon depends on epsilon hat. So you cannot say, oh, then I feel like I want to reduce epsilon hat. If you change epsilon hat, you have to change epsilon. Okay, so this is why we put at the beginning the conditions. Okay, but to prove this lemma, to state it, if you don't really want to use it exactly as you state it, yeah, you can forget about this condition. The really important thing for the lemma is this part, that you separate the two graphs. Okay, so it's just a lemma about Buzzi and continuity. That's so, and compactness to finish. And so it's really, but it's the key thing. So it's a little bit trivial, though I suffered somewhat. But the point is that you want to, okay, all our efforts are to say we start with double scale epsilon hat, we iterate a little bit, let's pretend n is equal to 1, and we want to recover the same double scale. Okay, so now let me see. Yeah, so consequence of this lemma. So are there any other questions about the proof? I will erase it. Yes. Okay, so corollary of this. Let me state it correctly. If we have any CR regular curve of the size with the epsilon hat given by the lemma, then for any, so when you iterate, well, it would be n, but as I said, you could think that big N is equal to 1. The diameter of the piece of the curve that is inside this open set stays above where it stays less than epsilon hat. So well, this is just rewriting the lemma. We don't care really about points. We care about pieces of curves. Okay, so that's okay. So now that we have this, okay, I need to now recall the thing about the lengths, because this here. So what I'm saying is that if we have some curve which is admissible, up to time n let's see, epsilon hat. Yes. Okay, now this has been chosen less than this than some constant. Then what I have is that when I look at the length of any iterate of this curve, then essentially its growth is bounded. In fact, it is given by the derivative at any point. So I have a small error at each iterate, is eta, which is the error I know myself. And then the expansion will be say it like this. And okay, I start with some length, which I know is less than epsilon. Okay, so for any tangent to the curve. Okay, why is this so? Just because the pieces stay small, so I can look at what happened at each iterate, and at each iterate, I have this, around each point, it's expanded according to the derivative in the tangent direction. But since the tangent directions are all very close to each other because of the admissibility condition, then all the values of these differential are essentially the same. So up to some factor close to eta. So I have this. I have this immediately. If I want to get eta small, you have to consider smaller and smaller curves as given by the modulus of continuity of f. That's just that. Okay, but the point of this is that it tells me this type gets the control of the direction at scale epsilon hat, which is somewhat large. And this tells us that if we keep the CR size small, then indeed the length will not only stay small, but will be bounded by the differential. Remember, our assumption is that we have a neutral block. There may be time where it is expanding. So it's not enough to say that to prove that at this time you are still at scale epsilon, it's not enough to say, okay, at time n-1, I was at scale epsilon, and now I have a contraction. You don't know that you have contractions. The contractions that you are starting from the beginning of the block. Okay, so this is why we write this simple estimate, to say that if these things don't grow, then the length will almost not grow. Okay, and then we can kill some small factor by subdividing our curve as long as it is some number which is exponential but with a small exponent. Okay, so now let me explain the inductive construction to prove the theorem. So we are going to divide. Okay, you have your curve here, and you want to cover the points which have this behavior that they are in a neutral block, and they are almost all the time they are in the set U hat where I have this continuity property, the lemma. Okay, so now what I do is I can assume each time I have a point in the relevant part of the curve. Okay, by definition, this is I'm only looking at points that define, or segments that define a neutral block. And moreover, they almost all the time, they are in U hat. Okay, so let me put in red the few times where they are not in, the iterate is not in U hat. Okay, this is the orbit segment. Okay, and now the usual thing I can pretend that these times, these bad times, they are fixed. Why? Because there are few of them. So you can call the type of x hat to be the location sorry, I should not do it like this. I'm going to. Okay, so now you want to divide this. Okay, I went too fast. So I had an accident. So what you do is given x, okay, you have this orbit. Okay, now what you start from 0, x itself, and now you ask yourself whether it is in U hat or not. Okay, so if this is in U hat, which will be the case most of the time for 1 minus gamma fraction of the time, then you will jump by big N. Okay, and why do you jump by big N? Because then you will be able to apply R2 lemmas. You can use the differential to control the piece of curve around iterator. Okay, so here, what do I? So, okay, let me first explain the structure of the induction, and then I will tell you exactly what you will do. Okay, if you are in a bad situation, which may happen, okay, since it happens rarely, you don't care, you just use your advance just by 1. And you use Yomdin local estimate, local one-step estimate. For sigma. Okay, for the piece of curve as before. When you do this, you will get. So in both situations, through different means, you will have Ri with a parametrization admissible okay, so you define this. Then you get this type, which is just this sequence of integers. Okay, when you stop when you reach N, or maybe N minus big N if you wish. Okay, so now for each point, x hat in the curve or in the lift of the curve, you have a sequence of integer that tell you essentially when you can apply in a greedy way the neutrality, or when you have just to use the fact that you have a smooth map with a bounded Lipschitz constant, and that's all. Okay, so the type will tell you, okay, you have maybe at first I have these are the integers. So now these are the integers. Okay, if I am outside of the good set, then I just increase by 1 and then I jump. So the thing you have to notice is that you have two types. Since to describe a type, you have to describe this subset. This subset is contained in the set of visits to the complement of U hat. So this set has cardinality less than gamma n. So it's you have a few choices. Okay, so the number of possible types is exponentially small on the exponential scale. Okay, maybe if this is the function minus t log t minus 1 minus t log 1 minus t. Anyway, it's a function that goes to 0 when t goes to 0. And we use a Stirling formula. Okay, maybe you need n to be bigger than some constant. Okay, but you get that. Okay, so you have few possible. The number of types is small at the scale of the computation you want to use. So now what we are going to do is just consider restrict to a single type. So instead of covering T that was given before, you cover, let's say, T of some type, okay, which are the points in T, okay, such that the type of the point is actually fixed. Okay, so you have a small number of such sets. So we are just going to cover any one of them, and then we multiply by this small number to get our final estimate. Okay, that's very standard. Okay, now we have to actually. So now I can state the induction hypothesis correctly. So I have a given type. Given type. So now I want to. So I want to parameterize over T theta. Okay, so I start at time 0. I just take the trivial parametrization. Okay, by assumption, is small. Okay, and now sorry, the assumption is here. Now I apply. I need to do one step, which can be of two different kinds. I will just do the interesting case. If I am in this case, so it means that I can, that my curve, so the image of my curve is actually contained in U hat. Sorry, not the curve, but the piece I'm looking at. This is contained in U hat. Okay, so now, so what I see is that first, I see that where is it? It's the corollary, yes, it's here. By the corollary, okay, the diameter of the images up to time big N of this. Okay, let me call that this curve tau hat. This is smaller than epsilon. Then I compute the length inductively, applying this formula. Okay, if at each previous step I have indeed built an epsilon hat admissible parametrization, then I can apply it. I have this, and so what I had for the iterate Ni. Now I want to make one step. Okay, but when I make one step, since here I am okay, I can okay, sorry. So let's assume by induction. Here I should say that the length of the curve, the image of the curve up to the previous step, reparametrized according to that previous step, and this was actually small, like when even insert. It's growing. I subdivide a little bit each step, so in the end I have something which is exponentially small with a small exponent. Okay, and given by the iterate starting from the beginning at any of the points of the curve in the piece of the curve. Okay, so now I want to extend this to the next. So this in particular, using the neutrality assumption, this is less than epsilon, and this one will be less than 1, and the whole will be less than epsilon. Okay, so now what I do is I use the continuity. Okay, use the modulus of continuity. To get to the following steps, when you do it, you multiply by the value of the differential. Sorry, not. You take the value in the direction given by y, but not this is the differential for f in the basis. Okay, when you use the differential, you in the obvious way, you get an extra factor from the fact that the differential varies along the curve. Okay, it doesn't vary too much because you know that at the previous step you were small, actually from the induction assumption. So you just have a small factor proportional, well, to nothing, to n. But you can kill it just by making, okay, I kill the extra factor by a small subdivision. Okay, so once you have this, you get that you have controlled the scale above, you control the scale below. Okay, so you can do this. What I want is the same thing for Ni-7. So for possible subdivision, this is the side. Okay, the same thing, but with Ni-1. Okay, so in particular, it's always, okay, so I have this. And finally, you use Yomdin with the double scale, but as I explained, it doesn't make much difference. So what you have done in the two steps is that you have checked that you didn't grow above and that you almost didn't grow below, but then any growth you could kill by a small number of subdivisions. Once you do that, you are looking at, you are applying a smooth map that you stay at a small scale, and Yomdin tells you, okay, you can reparametrize so that you keep the CR size less than epsilon hat at the price of paying at this kind of price. Okay, parameterize using the covering number. So you get here the covering number is small because you work that. Okay, so this is where you get your something like that. Okay, and so when you have done this complete the induction step in this first case. In the second case, it's essentially the same, but the two first steps are trivial. What you just say is that f hat is Lipschitz. So you start from you are inside an epsilon hat ball. You get to something where the epsilon hat have been multiplied. So you need to subdivide, but you subdivide by a constant term. Okay, and since anyway it will be multiplied by the frequency of this bad behavior, which is very small, gamma, you don't care. What you only care is that here you have a bounded cluster. Okay, which is like the Lipschitz constant of f hat, the power 1 plus 1 over 1 minus. Okay, this one is for the growth of the balls, and this one is then for the reparametrization of Yomdin. Okay, so you check that you keep the size and the length in this way, and you continue until the end of your induction. Okay, and once you have done this, you get the kilemma. Okay, so sorry for the mess, but so I will stop here. Everything was so clear.
Thank you.